part of this talk impromptu on Monday already, so I'll try to avoid any overlap. And maybe we can finish a bit earlier. So this is about a project we ran. Started about 10 years ago, and we took all the main proof assistants and we said, okay, we're going to export from them, and then we're going to do library integration and so on. So the whole work was part of a major succession of efforts. So Michael started developing Omdoc around 2000. The idea of Omdoc was always that it would act like as an interchange format between tools dealing with math. So in particular, the idea was that proof system would export to Omdoc, other people would import from Omdoc. Omdoc liked the formal semantics, which is something that MMT added by basically using Omdoc just as a file format in the background, but then adding on top a logical framework-inspired layer of specifying exactly the syntax and semantics of formal systems. So MMT mostly uses LF, but technically LF is just one logical framework in the library that MMT provides, and users can build their own logical frameworks, something that we heavily needed to, because logical frameworks generally still have to play catch-up with real-life purposes of logics. Most of the real-life logics cannot be represented nicely in logical frameworks. The first case study we did was a major research project, and coming out of my PhD thesis, we called it the Latin Atlas, where we formalized all the logics we could get our hands on using this technology. So we focused on the logics, so we didn't do the libraries yet at that point. And we mostly focused on the textbook logics, like starting basically with first-order logic, simply type lambda calculus, and then going from there. And in OAF, we said, okay, now that we have the logics somewhat under control, let's scale up and do the libraries as well. So the idea was that after manually writing logics in Latin, we would generate the library exports from the various proofs relative to those logic formalizations. And I picked the titles in a lesson learned style, so we ended up not doing all the things we wanted to do. So I'm first going to tell you what we thought we were going to do, and then what we actually ended up doing. How can we see this one? So the basic idea is you represent the language of the system S in your logical framework. And at the time, MMT and LF was kind of the default choice. Recently, we have seen Deducti and MM0 as alternative candidates for such frameworks, and the methodology will always be the same. And in fact, all three of these systems are more or less based on LF, so it's no surprise that the methodology is at least similar. So you represent the syntax and proof theory of the system in your framework, and then you export the library from the proof assistant relative to the definition of the logic. And then we thought that that would be like the first third or first half of the project, and that we would then be able to focus on integrating the libraries. Because just by exporting everything to the same system, you haven't gained anything yet. Right? So, where's the chart? Oh, yeah. So if you have disjointed libraries before, if you do this kind of before, what you have is disjointed libraries in the same framework. But you haven't actually done anything yet to connect these with each other. So we can think of this as a universal representation format that doesn't do any library integration. So the picture we ended up getting in the end, I've shown it on Monday already. So we have MMT as a main framework, in that we defined various logical frameworks, and then we represented the logics of various proof assistants relative to that. And then the digital laser pointer is not working as well as the old school ones. And then we represented various libraries of those systems relative to that. So this actually all worked. Quick example, maybe this audience doesn't need it. If you want me to speed up, give me a sign. So here whole light is one of the easiest languages to represent. So for a project like this, you can think of whole light as the hello world example. If you can't do whole light, you go back to the drawing board. So we have types, then we have terms of each type, we have proofs of each Boolean, and then we have the types, Booleans, function types, lambda abstraction, application, and equality as a logical formula. Equality is reflexive and transitive. There's a couple other rules which you can represent in the same style. So you always start with the syntactic categories, then the non-terminants of the grammar, the constructors corresponding to the productions of the grammar, the proof roots of the inference system, and then you're good to go. This works well for whole light because whole light is basically a textbook logic. It's using exactly whole as you would see it in a lecture or a textbook, contrary to all the other proof assistants which have lots and lots of additional, often very novel, very experimental language features.
Term missing.
Sorry?
In equal, there's a term missing.
Oh, quite possibly, yeah.
Sorry. Just slipped out.
Oh, no. So equal, I think, should have the type term parenthesis of A arrow, A arrow.
Oh yeah, I'm dropping the parentheses here, yeah. So this actually is not a typo, but it doesn't matter. That was the wrong button. What do I need to do?
Control L?
Is it touch screen?
So then we take the library. Here as an example, we have the type pre, which goes num to num. It's a predecessor operation. In MMTLF, this is represented as a constant pre of type fun num num, meaning it's a function type from numbers to numbers, and it's a term of that type. And in XML, that declaration then looks like this. This is the omlog syntax. You see, it's basically the abstract syntax tree with some angular brackets around it. So we have a constant with a name. That constant has a type. It's an application of the apply operator from LF, applied to the term operator from whole light, applied to the fun symbol from the whole light library, and then the num symbol from the nums module of whole light. So any export would produce more or less the same thing. The only choice is whether to use XML or something else, but it's always the abstract syntax tree as seen by the kernel that gets written out in some format. And then based on that, we can have logical framework-induced generic services. Here as an example is we render the whole thing in XML. We have intelligent user interface that, for example, can dynamically infer the type of sub-expressions without having to call whole light in the background, because the LF logical framework can do that for us. So we're completely separated from whole light. Once we define the logics and export everything, we can have quite a nice amount of services already. Here's an example of search that we implemented. Here the query is x mod p equal y mod p, using x, y, and p as pattern variables for the search. We have two hits in the whole light library with the matching subterm selected. And then what we wanted to do instead, in addition, we wanted to do logic translations. We already had logic translations in Latin. The idea is you have two systems represented, S and T. You have the translation represented in some way. In MMT, in Latin, we use theory morphisms for that, but you can come up with any number of other representations of translation functions. The key idea is you're going from expressions over here to expressions over here in a way that you preserve typing provability and stuff. So this works really, really well in theory, and it works really, really well for textbook logics. It has turned out to be a complete failure for practical proof assistants. So usually we already failed having good representations S and T in the first place. And even when we had them, it turned out that these translations were way more complicated as could be obtained with a nice declarative specification of the translation. So the motivation was that this would be declarative, maybe provably type preserving, provably terminating. And in practice, almost every translation you do, there's some subtlety that ultimately makes you throw everything away and use a Turing-complete programming language to get it done. It's frustrating because once you make that step, you lose all the nice properties like guarantee of invariance, guarantee of provability, guarantee of termination. Suddenly you have a whole another code verification effort just to prove these environments, which the logical framework would have given you for free if it were good enough to express the translation.
So, Florian, I'm, like on a surface level knowledgeable, but on a deeper level quite ignorant about these issues. Are you saying that LF isn't really like a Turing-complete programming framework, and like these translations in practice do need a Turing-complete programming framework?
Yeah, so LF 12 is, because 12 has a prolog-style programming layer on top of LF, and there you can do it, and 12 even adds features to then prove the correctness and termination of these translations. So, but it has fallen out of favor even in the 12 community. So Schurman has built Delphine in response to being unhappy with 12. Kienka has built Beluga, and I think the logical framework community, me included, is still researching how to come up with nicer languages. You don't want to go all programming language because then your verification problem explodes, but you can't do it just in LF because then you're not expressive enough. And we're like experimenting with different trade-offs in between.
But like the solution we heard from Frederick in Didacte is to have sort of a declarative Turing-complete framework by using rewriting, right?
The rewriting is roughly on the same level as the 12 logic programming, except Deducti doesn't have any way to prove type preservation and termination of the translation.
I can add something. So rewriting is used for the encoding of logics. It's not used to write any translation.
Oh, okay. But it could be used as a
The translations are written by, standard programs in OCaml or anything you want.
Okay, so you're also gone full programming language already, but because in principle you could use the rewriting, it's just, it can get annoying.
So it's used to some extent for some transformation between one field to the other, but it's not the main way to do it.
So what happens is, first, non-compositionality. I'm going to give some examples later. So if you do the nice translations in logical framework, usually the reason why you have all these nice properties that you can prove generically is that the translations are compositional. Meaning they go recursively through your input, never doing any nested case distinctions and so on. And almost all the time, your language S is going to have some feature that T doesn't have, and that T cannot define either. Simple example, if you have subtyping here and no subtyping here, of course you can't map subtyping to anything. Subtyping might be undecidable even, and then if T is decidable, you can't even map the typing predicate here to the typing predicate here. So you end up having to replace every occurrence of subtyping with a transfer function or a casting function, which means you have to keep track of that during the translation. Which casting functions have you already generated, which do you still need, and at that point you just want to use a programming language. The second big problem is, I indicated on Monday also, what we call the library integration problem. Even if you make the translation work, you still have the library integration problem, and it turns out when you want to solve the library integration problem, having a translation isn't even the most important part, and might even get in the way. If you are mapping every constant in the S library individually to the aligned constant in the T library, in a way you don't really need a logic translation anymore. You're already translating every constant individually. The rest of the translation then follows somewhat straightforwardly for all these alignments. So focusing on getting the logic-to-logic translation right isn't really the point to start. You should try to build library-to-library translations. And that's what we realized in the project, which we never got to. So here's some more examples of things that go wrong. So I mentioned the undecidable subtyping of PVS. So if PVS is your starting logic, that's one of the issues you're going to have to deal with. There's a bunch of others. PVS is maybe the most annoying in that respect. It has extensible records, and it has really messy theory inclusions. Let's see, partial functions and IMs. In general, any system with undefinedness is a problem, because most target systems won't have undefinedness, so you're going to be in trouble. If you want to go from a system with non-empty types, like whole, to a system where, not the other way around. If you want to go from a system that has empty types to a system that doesn't allow empty types, you're going to have to figure something out to deal with that. In a system like dependent type series, you often have propositions and booleans as two separate constructs. Now, if you want to go to something like whole light, where you only have one type of booleans, you have to think about what to do. You can merge them, but then you're messing with the types theory. Booleans and propositions are different in Coq. Merging them in the translation might mess things up. And the other way around, it's even weirder. You have one concept, and you might want to generate two different ones. And it's really unclear how you should decide when a whole light Boolean should go to a Coq Boolean, when it should go to a Coq proposition. Universes are a problem. Like if your source language has them, if your target language don't, you're going to end up with some encoding of universes. So all of these things are doable. So this is not like a fundamental impossibility, it's just that every translation has a couple of these, and every time it gets really, really messy and difficult. And it's not obvious what the best encoding is, and every encoding has some drawbacks, and every encoding induces some overhead. Like I call those encoding artifacts. For example, with subtyping, the encoding artifact is that in the target language you have these casting functions appear everywhere. Then the user of the source language isn't used to those, so you want to hide them as much as possible. So you end up with an extra layer of software to try to hide the encoding artifacts from the user. And then, of course, if it's non-compositional, it gets really, really brittle. Non-compositional basically means you do inductions on the syntax. That means every time someone adds a feature to the language, some of the nested inductions breaks, the whole translation breaks. They may work for some features, and if you combine features, non-compositional translations do not work well. If you're compositional, usually that works well. You can drop a feature and the rest works fine. If you have two features translated separately, you can merge them, it works fine. If the translation is non-compositional, you lose all of those. And then most of the time in practice, you're partial, because there's going to be some feature where you don't know how to encode it, or the PhD student who is working on it doesn't have time to do it, and you just drop that feature in the end. And you might think, okay, let's just be pragmatic, let's just have partial translations, that's better than nothing. And in some sense, it's perfectly true. But then very, very often, many of the most annoying features to translate are used very deep down in the library already. A simple example, if you have subtyping, you're going to use it for natural numbers are a subtype of the integers, are a subtype of the reals. That's like 101 in your source language. So if you say, oh, let's just drop subtyping, we ignore that, doesn't work. Already numbers can't be translated properly. So occasionally you have weird features, like maybe you can drop the records of PVS. If your input library just doesn't use records, it's still going to be good. But very often, dropping one of these features breaks everything. Because it's used somewhere, you can't be partial on these fundamental things. You had a question?
Oh, no.
Okay, so you looked very quizzical. Right. And now let's say the translation works. Let's say we have system A, and here we have system B, and our translation worked. Well, still what we're going to get is some kind of mirror image of A inside B. It's not what we really want, which is a translation that goes from A to B. So we still have two disjointed libraries. We just have now the image of the A library as a sub-library of B, but totally unrelated to the rest of the B library. So that's where the alignment comes in. So I think the first translation that did alignment was Stephen Obua and others. Whole Light to Isabel, 2006-ish. And since then, more and more translations have tried to do that. Generally, the basic idea is easy. You have a symbol in the source library, it has a definition. You just drop the definition, and instead translate the symbol to something else. Of course, it has to preserve typing. That's easily doable. But normally, you want to preserve the definitional equality also. You just discard that equality. Means you have to keep track of everything down the road where this definitional equality was used. Now isn't true anymore. It's doable. I think the best system I've seen was Kalishik and others, where they just introduced gaps in the target proof and then used the target system to prove the gaps. So that can be very successful that if you're introducing this defined symbol goes to some other symbol translations, you're breaking a lot of equalities. Just give up on trying to translate the entire proof. Translate the highlights of the proof, maybe the induction hypotheses and key lemmas in between, and then just hope that the target system can fill the gaps. That's how it should be done in the future. But as a community, we haven't really done it at scale and very well yet. Simple example of alignment. I've shown you that on Monday, so let's skip over that. And more examples that I've shown. So we have a couple of papers from like 5 years ago with Kalishik and others where we looked at, okay, what are alignments? What kind of alignments can we expect? Naively, we would think, okay, we just need to take symbol of the real numbers in card and map it to the real numbers in Whole Light and we're good. But in practice, what happens is that sometimes the function takes 2 arguments in the source language, but 3 arguments in the target language. For example, if division takes an extra proof that the second argument isn't 0. Or in dependent type theory, you usually have all kinds of implicit arguments that need to be inferred, whereas in a simple type theory, you just don't have those. So morally, the same function has even a different arity in different languages. Or maybe in the source language, the function is very general, like polymorphic lists, and in the target language, you just have lists and not monomorphic lists. So then you have to drop the type arguments one direction or infer them the other direction. So very often, you don't even get the typing right if you use alignment-based translations, and you can't even, it's not even easy to get well-typed terms out of that. Machine learning actually might be a way to go. If you train on the target library and then you give it a term that's roughly well-typed, maybe some machine learning tools can figure out how to mangle it to make it well-typed. I'm not sure if anybody has tried that. Yeah, so we can use alignments to get rough translations. Definitely at the proof level, where we should focus on high-level proof translations. And most of the time also at the expression level, where we get terms that are more or less the right term, but they don't technically type check. How to get these alignments is another problem as well. We have thousands of definitions in these libraries. So what do? There are some attempts to do it manually, some attempts to do it with machine learning. I've had a working group on that at a Dutch seminar a couple of years, last year I think. We managed to again, spell out the challenges, but did not make major successes. So, but one of the ideas that came out of that, which has now been picked up by Katja and Freyk, is this 1000+ theorem thing, which in a way is an alignment at the theorem level at least. And maybe if we're aligning at the theorem level, we might realize, hey, let's also align the constants occurring in the statement of these theorems. And that might be a way to get larger numbers of alignments so that we can actually evaluate which of the translation methods work well. Because currently we don't even have enough alignments to test the ideas how to translate. Yeah?
Or maybe we'll realize every single one of those theorems in each system means something different, and they're not the same theorem.
Yeah, I didn't even mention that, yeah, but very often the problem with alignments is that the comments imply that it's the same operation, and the name is maybe even similar, and the type might be similar, but still it's not the same. Division is a famous culprit again. Just checking what division by 0 does in the various systems gives you like 3 or 4 possibilities, from being undefined to being 0 to I don't know what else. Yeah, so operations might do something else. So even if you get well-typed results, they might mean something else, and you might not be able to prove the translated X. So an idea of how we think it should be done in the future is be more axiomatic. Have axiomatic interfaces that specify the data types and the theorems you want to translate, and then think of 2 proof assistant libraries as 2 different implementations of the same interface. Going from the interface to a proof assistant is easy, and then of course we have partial inverses. Those will be difficult, but my prediction is it will be much easier to have partial inverses from a proof assistant library to a stack of some of the data types in it than it is to have a direct translation. But this also has not been tried at scale. I think Deducti is doing something like that. You have like the arithmetic hierarchy in Deducti, and then you have different copies of the hierarchy in various proof assistants.
No, this is not.
Okay, but you're close. You could do it.
But I don't think we are going to do this.
Yeah, but
Because the problem is here so who is going to decide on the stake?
you write it, for example, in your case in Deducti, from scratch in like first order logic. I've seen some talks by Jill where he says most of the math works in first order logic, so let's just write stuff in first order logic. That would be here. And then we have images of those in much more complicated logics here. You might not be going to do it, but it's a possibility. MMT could do the same. We have written out interfaces here and then did some of these partial translations in prototypes, but nothing at scale. So I'm running out of time. Let's just drop this and talk a bit more about what we ended up doing. Most of the work was spent actually doing the exports. So all the nice library integration theory, we didn't really get to it. And we needed massive help on all of these exports. So we worked with, for example, Claudio and XML, with Macarius and Isabel. That was alone like 6 to 12 person months just for one export. And that was with me and Macarius working, and both of us had extensive experience. Macarius and Isabel and me on how to do exports in principle. For a PhD student team, this wouldn't be doable, or wouldn't have been doable at the time. But one positive outcome of this project is that the export technology has become a lot better. So partially due to this work, Isabel now has really, really good export capabilities. We were the first people to actually use the PVS export and fix all the bugs in it. So Sam was very grateful to keep updating the PVS export. Misa has, partially due to the collaboration with us, partially due to other reasons, completely redesigned the XML export, making it much better. We actually redid the Misa export a couple of years back, and it was then possible for a master student even to re-implement another export from ESA. And so I think Lean, which at the time wasn't big enough yet to consider, has learned from this already and has started out with good exporting capabilities. So, and this was in a way always the end game. Like, it doesn't make sense that other people maintain exports from proof of systems. The proof of systems themselves have to maintain export capabilities that other people can then connect to. Actually, I want to draw a picture of that. So you might think that you have the proof of system library here, and look at this, multiple of them, and then here you have the framework, which could be MMP or MM0 or Deducti. And you want to have encodings going here. That's the natural way how people might start developing an export. Take the proof assistant, go through the library, export it in whatever framework format you want to use. And one main realization we had is that this does not work well and should not be done at all. Instead, every proof assistant should have its own export, and then you should go from here. So it doesn't really matter which format this proof assistance export is in. Like in Isabelle, it's heap images or database or whatever, and you can just write your own traverser of that to whatever you want. In Coq, you have the binary files, in Lean it's the same, Misa has its XML files, PVS has an XML export. So all the systems nowadays have these kind of exports, and those are the ones that outsiders can walk over reasonably well to then produce whichever interface format you want. So the main lesson that we learned here was that what should go into this export, what should it look like? One very important property, this export should not do any encoding of the language. It should give you the exact abstract syntax tree in the system. All the non-trivial encodings could then happen here if necessary. The second thing is, well, it should be well documented, of course. Systems working on that, they're getting there, it seems. So that an outsider can understand what that stuff means. Thirdly, it should have source references, meaning every node in the syntax tree here should tell you where in the source that stuff was declared. So really, we should think of a proof assistant as a compiler here from source to kernel AST. So there should be source references that point back to the node in here. That's really, really important for many tools you want to build on top of these exports.
Well, you probably know yourself that this is not always fully possible, right? Like if you're,
Yeah, that's the next thing I was going to say.
Yeah.
Most proof assistants have a highly non-trivial translation from here to here. Like in the olden days, this was mostly type checking and some type inference, and you were done. But the development in the last 10 or so years has been that this step has gotten more and more complicated. Things like Isabelle, Coq, Lean now have highly substantial elaboration algorithms that go from the source that the user sees to the AST that the kernel sees. Yep.
So I do like this diagram. Can you push the up? I do like this diagram when you put this bubble before the kernel, because this is what we were discussing, I was implementing, but I did make some changes there. So the kernel, the internal kernel representation is not what is exported there. So I sanitized it. I make this exportable. So changing certain internal representations. And this is why it required so much manpower there. Yeah. I had to go back to kernel implementations to make this exportable in the first place.
Yeah, and I think this is typical
of things and so on.
If the kernel was written without export in mind, which is true for all proof assistants, you won't get the right thing right away. And typically you have to go back, in the worst case, change
the most basic change is the kernel is deploying without names, and I export it in a way that it's up to you to choose. Do you want deploying or do you want named bounds?
That's a good thing, yeah. Structure sharing is another one. Sometimes systems have trouble exporting in a way that preserves structure sharing. So we actually had COG export situations where it just timed out because there were some mass comp proofs that were too big to print. Another thing, yeah, so this is highly non-trivial. So the AST here, that the user thinks the system is providing, is an entirely different one than the IST here. And usually this one is a much simpler language. So these are by the example, here you have inductive types. The kernel has no idea what an inductive type is. Here you have locales. The kernel has a very vague idea what a locale is, but most of the information that the user thinks they have formalized is gone here. So Macaris actually did some reverse engineering of the elaboration to give us some locale export back. So typically, what you would really want isn't even this. You would like to have, I don't know, like this, and then go from here. Like the actual source AST that the user thinks the system is maintaining, with all the types inferred and everything disambiguated here, and completely drop the elaboration, because what the kernel sees isn't relevant for library integration. It might even get in the way. Because you want to preserve the high-level features like inductive types and locales. Those you can use meaningfully in the target language by mapping inductive types to inductive types, for example. So this is what I would really want. No system is coming near here, except for the ones that don't do anything difficult here. Like in Holite, you can kind of get it because it doesn't do this so much, but then you don't have the expressive input language that the user demands either. I'm running out of time, but this is as good a point to stop as any.
Okay.